Chris Phillips from University of Oregon, and Chris is going to talk about the simple AH algebra with the same Elliott invariant and the radius of comparison. Yes, Chris.
Okay, thank you.
Please take the floor.
Yes, so I should say two things. One is this is joint work with Elon Hirschberg. The other is when I was preparing this talk, I wasn't actually sure whether I was supposed to be preparing for 1 hour or 2 because I didn't hear back. So I actually have enough for 2 hours. If people want to hear about some details of how to actually make things work, I can either continue later in the after Grazie, you're next, is that right? Or not, as may be of interest. Okay, so I'm going to state some theorems without definitions, which I will give later. So I want the Elliott classification program. And I didn't write down how many people to attribute this to. I mean, there's at least 10 and more. But anyway, the theorem is this. Let A and B be simple, separable, unital, nuclear, sister algebras satisfying the UCT. And with isomorphic Elliott invariants. Which I will state later. Then if A and B are Jiangsu-Sable, then A is isomorphic to B. And let me also state the version if A and B have strict comparison of positive elements. I should say many people. And the extreme boundary of the traceless state space of A, necessarily then also of B, because it's part of the Elliott invariant, is compact and finite dimensional. Then A is isomorphic to B. And according to the last remaining case of the Thomas-Winter conjecture, this should be unnecessary. But that's still okay. I think it's a couple of special cases outside that are known, but in general, it's still open. Yeah, this is the one I actually want to refer to today. And then Tom's in 2008 showed that strict comparison is necessary even if you include things like stable rank and real rank and so on in the invariant. So in fact, constructing, in fact, there exists an infinite family of I'll put here, or I should say, I'll again define this later, of first type. Pairwise non-isomorphic. In fact, distinguished by the radius of comparison, which is another of the things I will define later. With the same Elliott invariant. As you'll see, these things are simple AH-algebras, and therefore, in particular, nuclear satisfy the UCT, and so on. Okay, but now we have a theorem. Yes.
So the strict comparison of what the element is a necessary condition. And you said also that according to the Thomas-Winde conjecture, also the condition on the stream boundary of the threshold state space is necessary.
No. So I've really stated two versions of the theorem here. First, that's one version. The second one is that if I replace that with this, then the Thomas-Winde conjecture says this one implies Z stable. No, that's not known to be necessary. If it were known to be necessary, that's what I'd be talking about.
But then the examples, that is not true, right?
And the examples don't have strict comparison. The radius of comparison, strict comparison corresponds to radius of comparison being 0.
Yeah, but also that second condition also breaks, right? Like the
That's also true. Yes. Yeah. I mean, the things we got are the Poulsen simplex and related stuff. So theorem, and what do so here it is. This is Elliott, Lee, and New. Preprint. And it says this. So here's the particular case I want. Let X be finite dimensional metric contractible and something they called solid, for lack of a better term. Let A and B be Villin's algebras as above, which I didn't define yet. With seed space X, which I'll also describe. Then if the Elliott invariants are the same, and RC of A, radius of comparison of A and B are the same, then A is isomorphic to B. Now, I think they said in their talks that, in fact, you could also vary the choice of the seed space as long as it satisfied these conditions. But I couldn't find that in their preprint. So I'm not sure what the actual status is. And since George is not here, I cannot ask him. So our theorem is to show that you cannot just use the radius of comparison as to undo the conditions here. So what we have is this. So its theorem is not surprising, but you certainly want to know that this happens for the purpose of understanding what the landscape looks like. Let R be in 0 infinity. Actually, later in the talk called it omega, so let me do that. Yes. So in this theorem, in your preprint, it says you fix the seed space first. But I think I remember hearing you say in the talks that in fact you don't have to, as long as if you take two of them, which are metrizable, finite dimensional, and contractible and solid, then the same conclusion holds. Is that right? Or
halfway there.
Halfway there. All right.
It doesn't matter whether you look at X or X to the D for arbitrary finite D.
Yes.
At the same time. But also there's even slightly better than that, because for any two contractible spaces, contractible metric spaces, the infinite products are the same.
Yes.
Okay, so the finite products you can throw in, but the infinite one, if you could, then they would all be the same. But it's a question of happening.
Yes.
1, 2, 3, 4. You go off, knew exactly where the difficulty was. 1, 2, 3, 4.
Yes, I remember that book from what, 60 years ago or something?
Well, sure, but, well, it was my introduction to complex analysis, so it,
Uh-huh.
defined the treasure on the island, even though the landmark is not the baseline because disappeared.
Yes, I remember that one, actually. Okay. So here's our theorem. So then there exists uncountably many pairwise non-isomorphic simple, separable, unital, nuclear. Well, this is redundant because I'm going to say in fact, AH-algebras. I'll put UCT in here. With radius of comparison equal omega. Same Elliott invariant, the isomorphic Elliott invariants, but not isomorphic. And they are really some sort of what I call multi-seed Villin algebra, and they are distinguished by a sort of local version of the radius of comparison, which I will be at least implicit, although maybe not. Maybe that'll be only in this half of the talk that will fall out because of the change of schedule. Okay, so some definitions. Elliott invariant, I'll just give this informally, consists of K0 of A as scaled ordered group. K1 of A, this is a group. Tracial state space of A, and the pairing of K0 of A with the tracial state space of A. I'll mention here, so note, today, all C-star algebras will be nuclear, and therefore we don't have to worry about quasi-traces. Well, okay, I should say during this talk, I'm sorry, I don't know what you're going to say, Kratzy. I didn't even look at your title yet.
Case that, in the Z-stable case, the scale, the scale or the scaling is important, but the order structure is redundant.
Yes. All C-star algebras are nuclear, so no need to consider quasi-traces. All right, so that's this. So second, I want to tell you about radius of comparison and so on. I want to go over some preliminary stuff here. Definition. Okay, so this C-star may not be nuclear. But A and B are in the positive part of it. Then A is sub-equivalent to B if for all epsilon bigger than 0, there exists a B in A such that norm B star minus A is less than epsilon. So it's sort of an approximate version of comparison. For projections, it comes down to usual Murray-von-Neumann sub-equivalence. And then for tau in T of A, and A will now be in, let's say, K tensor A, positive part, or I guess here it doesn't really matter. We'll extend tau in the usual way to these things. D tau of A equal the limit as n goes to infinity of tau of a to the 1 over n. This is basically the trace of the open support of A. And if A is C of x and tau comes from a measure mu, then in fact, this number is in fact the measure of the set of places where A is not 0. And then A, and now it should be unital, has our comparison. And here R is in, let's say, 0 infinity. If A and B in K tensor A, and again, you can use M infinity of A and Z, it turns out to give the same answer. And d tau of A plus R less than d tau of B for all tau in T of A implies A is subequivalent to B. So it's like strict comparison of projections, which has been around for a long time, except now you use positive elements in this notion of comparison. And then we will say, so definition, RC of A is the inf the set of R. A has R comparison. And I want to get note here that this is, so if A is not what's called residually stably finite, so caution, this means that all quotients are stably finite. Then one should not use this. One should use instead the R sub A. Following bucket R, etc. Well, 4 or 5 other authors. But here, this will always be satisfied. In the C algebras we consider. And on this class, the R sub A is the same as this. But in general, this is rather better behaved. Okay, so that's pieces of invariants. And now I want to talk about pieces of algebras. So here, so now take X to be a compact, I guess, Hausdorff space. No, it's the wrong page. Here we go. Then I guess I'll call it for today. I like a better term for this. The naive. I need a sequence. D of n in n. So this does not include 0 today. I got once told by somebody or other that there were 2 kinds of mathematicians, ones that insist that 0 is an element of n, and ones who insist that it is not. Logicians tend to fall in the former camp. I look back at papers I've written, and I've adopted one convention or the other, depending whatever happened to be convenient in that paper. Yes, well, okay, you write a paper, you better actually say, though, what you mean. Right, if you use a symbol in your paper without explanation, then people aren't going to know whether 0 is included or not. Of, let's say, parameters. Let me just call this D. X and D is the direct limit of the following system. I'll take C of X to C of X to the D of 1, M D of 1 to C of X to the D of 1, D of 2, M D of 1, D of 2, to etc. And let's abbreviate this thing here as, let me specifically point to this one. This is going to be S of 2. This is going to be S of 1. With maps, so this is going to be from C of X. So it's going to be X to the S of N, that's the nth algebra, M S of N, to C of, and now I'm going to put in the next thing here. So I'm going to write it like this, X to the S of N to the power D of N plus 1. So the total exponent here is S of N plus 1, M S of N D of N plus 1. So this is, of course, S of N plus 1. And so what are they? I will simply take, so F maps to some diagonal matrix. And what is it? It's F composed with P sub, I guess I should put n comma 1 here. So Pn1, Pn, and there are, so what are they? I'll put the index in a moment when you can see what I want to put there. So these are from X to the S of N to the D of N plus 1, just to X to the S of N. So at least the map the spaces the right way are the coordinate projection maps. And now you can see I have to have D of N plus 1 of them here. So under good conditions, this algebra will have radius of comparison dimension of X. Sorry, half the dimension of X. Things can go wrong. There are compact metric spaces X, such as X cross X has dimension less than twice the dimension of X, in which case this will be smaller. Nobody actually knows. I guess for that case, we can figure out. Oh, and I have to put up here what the rest of the things are. F composed with P, N, and D of N plus 1. Okay, but it's not simple. Okay, so we point in some point evaluations. Suitable point evaluations. And so let me cross this off and put F of, let's say, X N1 times the constant function 1, F of X N, and okay, to match notation with what I'm going to use later, let me put here L of N minus D of N. And I have to multiply the constant function 1 there. So the total is now, now I have to put here, of course, I'd better put, where I put it, it's up there. Now I'm going to have to multiply here by L of n plus 1. And now I will need matrices of size R of n with R of n being the product from 1 to n of L of k. Because after all, I can't just fiddle it at one stage, I have to fiddle it everywhere. So these numbers are different all the way out.
Where do you want n plus 1?
It's a notational convention. It's not clear that was the best one to make, but that's what we wrote in the internal asymmetry paper and in several later papers, so I'm sticking with it. Oh,
Have n plus 1 coordinates.
D of n plus 1 coordinates.
Well, D of n plus. No, but you goes 1 up to D n plus 1.
Yeah, no, this just indicates what level I'm at. So the n, so this is from n is for an to an plus 1. And that's
Starts at 0.
n is going to start at 0, but the d's start at 1. So A0 is C of x. Yeah, I mean, you see, when you go from the n to the n plus first one, how do you label things?
I think it's
There's
right now it's understandable what's happening.
there's always I should probably put n plus 1 comma n here.
I think notation 3 approach to that.
Yeah, well, I want to at least get them. I mean, I've got to. Okay, I better say at least that much, and I better say this.
How many evaluations do you need to add?
You can so you can make it simple with L of n equal d of n plus 1.
I didn't know. You have to help with meaningful algebra A. The only important thing is have to do. All right. Then you look at say 2 by 2 matrices over A, and you map A into 2 by 2 matrices over A, and you do it by putting A tens over A tensor A, 2 by 2 matrices over A tensor A. And then you have A into the L, and well, the algebra A maps into the matrices A tends to 1, 0, 0, 1 tensor A. Now that's
Yeah, so that's what the naive one is. So this is the direct limit. So A0 equals C of x, and then you have A0 to A1 equals M something or other of A0
coincides with those, but just
tensor, et cetera, tensor A0 with the same number of tensor factors here.
but my point is the notation is it can be self-administered. You don't have to
Well, I'm going to need limits of these things eventually. So
don't want everyone the Tower of Babel, everyone has difficult things.
yeah, well,
Having read several papers about Phillips and algebra.
okay. So that was that. Okay, and then finally, the last thing which goes into the algebras. This is just a matter of convention. Should say convention. So definition. X is solid if for dimension of X equal D, there exists a ball, a closed subset homeomorphic to a ball of dimension D. Closed ball. Dimension D. So this is in particular guarantees. So in particular, dimension of X to the M is M times the dimension of X. And for everything which is actually done here, it's entirely possible, in fact plausible, that one can replace this condition with, say, the rational cohomology. Oh, sorry.
Yeah, do you want the Ln plus 1 minus the Ln plus 1 or Ln?
I think I want L of n. Because I'm going to take, if I use 1 point, I'm going to say L of n is D of n plus 1. And so that will be 1. And that matches that.
No, but I said, do you want the Ln plus 1 minus
Oh,
the Ln plus 1?
yes, I do. Yes, thank you. I think I have the right number of parentheses now. So over here, it's probably enough to say the rational cohomological dimension is equal to the dimension. Okay. So our examples use a sort of gluing process or procedure. And so the general way I want to format it is we consider a multi-seed. Oh, I forgot to say one thing here. X is called the seed space. Multi-seed Phillips algebra. And so basically what we do is we take systems like, well, this modified version here with those things appropriately changed, but we take M of them, and we allow maps to go sort of crosswise between the different parts of it. So the ingredients are spaces X1, XM. This is for M seeds. And let me get the notation at least to be the same as what I have elsewhere. We have sequences. These will be the exponents. dj of n. That's n here. And set sj of n, the product from 1 to n of dk. Sorry, k equals 1 to n of dj of k. Those are going to be the exponents on the spaces. Partial embedding multiplicities. I probably should write up the diagram before I actually put notation. And this time I'll write it vertically. I've taken to usually writing Brotherly diagrams horizontally because they take up less space on the page if you do it that way. But for this one, it doesn't help so much. So we're going to take A0 is M R of 0, or 1 of 0, of C of X0 directs, oh, I've been using different notation. Sorry, let me go back to.
We managed to do a bird when you introduce Jones's interpretation of the multiplicity references as Coxter diagrams, and those lay out flat, which is how we usually.
Yes, well, you simplify in one place, you cause problems elsewhere. Happens a lot. X2, MR2 of 0, direct sum, etc. Direct sum C of XM, MR M of 0. And I'll just write one more. X1, now it's going to be the S1 of 1. And this is going to be MR1 of 1. C of X2 to the S2 of 1. MR2 of 1. C of XM to the SM of 1. MRM of 1. And so I have, right, I'm supposed to have a map like this. It decomposes, and there's partial maps going every which way. And then each of them has a multiplicity, just in terms of matrix sizes. Mu kj of n. So here j and k are 1 up to m. And we need it. Here I'm going to have enough space for all these projection maps. And so I need to have with mu jj of n bigger than or equal to dj of n. I'm not going to, yeah, you want me to assume strictly bigger?
No. Okay.
If I take one seed and put equal there, I'm going to get exactly this naive Villin algebra without any way to make it simple.
Sorry, they are.
So, yes, so yeah.
And are like treated like that.
Yeah, so the Rj of 0 is fixed at the beginning. Part of the information goes into the construction. And let's say k of n plus 1 is, so this map is supposed to be unital. So it's going to be equal to the sum from j equals 1 to m of, now I need mu. Is that what I called it? Mu, yes. K comma j of n plus 1 times Rj of n. So think of it as just an AH-algebra diagram gotten by taking all the spaces to be a point, and set up so that these mu's are the labels on the arrows in the broadly diagram, and they're supposed to be chosen so the maps are actually unital. And here this should really be S1 of 0, but here Sj of 0 is 1 for all j. There's no particular point in choosing arbitrary things there. I can simply change the space instead. You'll see later why I want to allow those to be arbitrary. And then the condition, the maps. condition of the maps. Is that the partial map Pjj n plus 1 n. So this is, I have a pointer around here. Yes, this was a pointer. That's things like this one and this one, but not counting anything that goes across. I'll say is, but of course should be just up to isomorphism. Diagonal of f composed with p something comma 1, f composed with p something comma, what should it be? It should be s, no, it should be d j of n plus 1 and other stuff. Like point evaluations or whatever. Also, I should put a 0 there because I want room for the codomains of the other ones. And this blank should be, so this is p n, no, j n and k for k equals 1 up to dj of n plus 1. And this condition here just says I've got enough room for that. Well, the other stuff could be, this could be the empty set.
Don't quite see these actually are different from what you're hoping reduction coordinate reduction.
Oh, no, only when the indices match. Only in the vertical things.
Yeah.
Otherwise, I can put anything at all.
I'm looking at project sums where you have the same x in different places, and all the coordinates have the same x number. Just is a natural way of having coordinate reduction.
Yes, and the examples are actually going to take m equals 2, but I wanted to put the general case up so as to just indicate what the situation is.
What's that?
M is the number of these things.
Okay, but we're looking at the case where n is just 1.
Yes, okay.
No, well, I mean, no, you're looking at the case where m is anything, but just the spaces are all the same, right?
Well,
But you're looking at arbitrary large
Oh.
sums, right?
of course, yeah, so, no, yes, well, that's, sure, yeah.
So can you explain that last part again? So are you saying that there's sort of no, like, what does it mean to be anything? Like, what does that mean?
So all I do is fill this in so that it lands in orthogonal corners which add up to 1. So
So like in your construction, you're just like when in those specific examples, right?
yeah, yes. So in our examples, these are all point evaluations.
So can you make just these maps can be any is 0 anything? Can they just be 0? Like the ones in between different seeds?
Well, so if I write it carefully, then I have to say that, sorry to hide that, right? This is a map. This thing, the partial map sends this to some corner of that. And if I actually write things carefully, I have to put a 0 here that's exactly the right size to accommodate the images of that one, this one, and all the others.
So the condition is that like you just need them to like you still want unitable maps.
I still want unitable maps, yes.
So those are just fixing stuff so that they're unitable, right? Like the DKJs for J not equal to K.
Yes, that's right. Yes, they have. Yes,
But
but
other than that, it can be anything. It doesn't really matter.
that's right. But in our examples, there are point evaluations.
Wait, how can you have a point evaluation from between two different spaces?
Oh, so for example, I could take phi 2 comma 1 of yeah, right, yeah, right. So of f of say 1 0 of f of y is just f of so this should be of say x for some fixed times identity for some fixed x in x1, and this is now something, but this is a function on x2 to the s of s2 of 1, right? Yeah, so you always put point evaluations going across. I'll try to do stuff like this with equivariant for group actions when the group isn't finite. Now you get in trouble. The group is finite, you can take direct sums of evaluations on orbits, but when it's infinite, then you find you can't make such maps. Okay. So where did I get to? Yeah. Yeah, so I'm going to assume always point evaluations here. And a weaker condition always diagonal maps. Okay, and so then what I will do is I will define when should I stop, by the way? Just a few minutes.
Sure.
Yeah, sure, that's fine.
Just so that the thing was gonna happen.
Yeah.
Are you gonna explain? Are you gonna have time to explain the local?
Very briefly, yes,
Because I guess that's the most exciting part, right? That's the way you're
Yeah.
gonna tell them apart, right?
that's right. Then RC of A is the maximum. You have to use some theorems and so on to do this, the maximum of kappa 1 to kappa m. Right, this is basically so I want 1/2 here. And I have to, and I'm missing stuff here. I did forget about the dimension, but I wasn't supposed to. Wasn't supposed to do that. And again, I'm assuming here that x1, xm are solid. Okay, so if we choose things carefully, then K0 of A, then, okay, so first of all, I want all the spaces to be contractible.
It's gonna matter that they're like, where are you? How are you gonna use that they're different, like the X?
I'm not.
It's the same.
Yeah. So I'm gonna, so let me just say this. I'll take m equals 2, x 1 equals x2 is 0, 1 to the power h for some h. L of n, L1 of n is sorry, I want yeah, L1 of n is d1 of n plus 1. d1 chosen carefully. And mu j, the matrix of mu kj is this matrix. It's got one thing across, And here I'm just going to put d1 of n and d1 of n here. And I take 1 less than or equal to d2 of n less than or equal to d1 of n. So that means that on this, in the second column, I've got more space here. And I'll fill in the rest of the space with point evaluations. Blank. Things. Point evaluations. And then one gets K0 of A is an ordered group. Q direct sum Q. Order. So positive elements are X, Y, greater than or equal to 0. If and only if X equals Y equals 0, or the condition should be X is bigger than lambda absolute Y. And lambda is some parameter. Lambda depends on the d1 of n only. And K1 is 0. And the tracial state space is the join of two copies of the Poisson simplex. Join, I won't take the time to define it now, but it was in the last talk I gave for entirely different reasons, having there to do with classifying spaces of finite groups. Okay, so what happens? So one is that the sending class of P mapping to the radius of comparison of PAP is well defined, first of all, on B of A, but in fact, on K0 of A positive part, because A is cancellation, because A is stable rank 1. This is Elliott whole terms. We want lambda bigger than 0. So then K0 of A as scaled order group has a unique non-trivial automorphism. By the way, this is the local radius of comparison. And I should mention that Elliott's ideosophy is looking at stuff which is related to this, but when you replace projections by positive elements, as unique automorphism, which sends the class of 1, 0. This is now in A0 to the class of 0, 1. So over here, now just got this part, I just got that part, and that's 1, and that's 1, and those two spaces are the same. So if two of these are isomorphic, call this thing, say, E1 and E2A. So if say A and B are of this form, and A is isomorphic to B, then RC of EA1, EA1 is RC of E2, sorry, E1B, B E1B, or RC of E2B, B E2B. And then the point is, given the choices of D1, for given choices of D1 of n, now we're going to choose D2 of n, the sequence, so this does not happen. This is all the stuff I've put on board so far, except for those radii of comparison. Does not use actually what D2 is. Okay, how to compute these things? So to compute, well, it's messy because various stuff comes up, but E1A, or EKA is again a 2C Villin algebra. However, sorry about having to hide this board. To make that apparent, you see I've tossed that entirely. So I have to start here. And now that matrix size is 1, and that one's not 1, which is why I wanted to allow arbitrary choices along there. For the choices of which choices? Okay, so to keep things simple, when I do my original algebras here, both the A and the B, I take those things all to be 1. So the 0 level is just C of x1 direct sum C of x2, etc. Commutative, yes. Now, this is going to be my, in some sense, dominant column, although it actually ends up backwards in the end. But this is the one where I'm going to choose the large powers of the spaces. I choose those large powers in such a way as to make and also the space, which is some interval in order, some cube, in order to make sure the radius of comparison is omega. Okay, you have to do something a bit tricky if omega is less than 1/2. But never mind. Then, and I also do that in such a way that this number lambda, which I did not describe, where did it come from here, is not 0. And in such a way that I actually get Q direct sum Q here instead of some subgroup of Q direct sum Q. That's really mainly for convenience. It's annoying to do that, but more annoying to deal with other stuff here. Given that determines K0 as ordered scaled group. The tracial state space is the join of 2 copies of the Poulsen simplex. You have to work for that too. It determines the radius of comparison of A. And also turns out it determines the radius of comparison of those ones, the E2 parts, but not the A1 parts. What's left to choose is the D2 of n. And I choose the D2 values of D2 of n to make those parts different. That's how we show non-isomorphism. Right, if I want the, in particular, I should have put down here the 2 and sorry, the 1 and the 1, yeah. So these things are not the same. Well, I have to produce examples to show that that happens, and we did uncountably many of them. So we want a choice of values with some parameter in it. Yes. Uncountably many. Essentially, by saying that given, so all the way up to the choices of up to the point just before I chose the D2 of n, that's determined. RC of E, of course, E2 A E2 is the same thing. And then I show that there's some interval of possible values of this, such that every value in that interval occurs with some suitable choice of the D's, of the D2 of n. And doing this is somewhat of a mess. And if you want to prove any kind of exhaustion of invariant result, then you'll have to do things like what we did, only in much greater generality. I mean, I didn't say what the interval is, but the interval is not everything. No, there are, right, there are restrictions on what this can be, which are forced by the other choices. Also, we want to make the choices in such a way that this one is the larger one, at least for convenience. Sorry, so that this one is the larger one, at least for convenience. So we can say what, no, it was this one, sorry. It was this one's the larger one. So we can say what the radius of comparison of the corner actually is.
But you know, this reminds me of Pierre Trudeau. Someone was complaining about the French on wanting a cereal box. And he said, well, why don't you just turn the damn box around? So turn your...
Yeah, it's funny. You have to, right? You sort of expect that yeah, you expect the two things here to play the opposite role from what they actually do.
Richard, what complaint with Trudeau?
It was some constituent, some citizen, some anonymous.
What did they complain of? What did they say?
Well, they look. Everything has to have both French and English on it, according to as legislated by Pierre Trudeau. Okay, but this guy was particularly annoyed by the breakfast cereal box.
Okay.
It was first thing in the morning.
Well, I have seen on the campus of the Ben Gurion University one of these sort of yellow warning sign things of the sort of stand that looks sort of like a small version of stepladder, but really isn't. Well, with something like keep out or whatever because of construction hazard or something like this. And what was written on it was in English and Chinese, but not in either of Hebrew or Arabic.